Hi everyone, welcome back to my YouTube channel. In the last video, we discussed everything about plotting in MATLAB. In this video, we'll be learning about Symbolic Math Toolbox, which is a very powerful toolbox provided by MATLAB. So let's get started. First, the basic definition of variables. So let's say I want to define a1 equals to 1 by 3. So this is the value of a1. If I want to define it using Symbolic Toolbox, then I'll use sim command. Sim bracket 1 by 3. Now see, instead of 0.3333, I am getting 1 by 3, which is the actual value. So now if we compare with whose command, then we'll see A1 and A1 sim. First one is a double and the second one is a sim. Sim stands for symbolic. Similarly, if we want to describe some complex variables, we put it inside a bracket with double parenthesis, where we are getting this value. Now we come to the most important part, is variable precision arithmetic. By default, MATLAB uses double precision, but sometimes it happens that double precision is not good enough. Let's say the double value of log 2 is 0.6931. So if we apply VPA on log 2, then we will get a much accurate value than a double. So this is a symbolic value. You can see on the right hand side, we go to VPA on double, it says 1 cross 1 sim. So it means it's a symbolic value. Now let's say I don't want so many digits, I only want 17 digits. So these are the number of significant digits that one needs. So I'll just separate the value by a comma and write 17. Similarly, if I want 20 digits, I'll write 20. Now instead of assigning some numeric value, if I want to create some variables, now sims x means, now x is a symbolic variable. Similarly, a is sim a 1 to 5. This means that we want 5 values of a. A1, A2, A3, A4, A5. Now, similarly, we can also write like this. Instead of like this, we can also write like this. Now, we want to multiply these variables to get something else. Then I define a small variable sims a with no subscript. And now I create one function which is a times x squared plus b times x. Now a is only a single valid variable while b has 5 components as described above. So f1 will have 5 components, as you can see, ax squared plus b1x, ax squared plus b2x, ax squared plus b3x, ax squared plus b4x, ax squared plus b5x. Similarly, if I multiply capital A instead of small a, capital A, if you remember, it was 5 variables. Now instead of having all the same a's, it will be having different a's. So a1x squared plus b1x, a2x squared plus b2x, a3x squared plus b3x, and so on. Now after defining these variables, how do we substitute and solve this? These are 2 types of variables that we can define. First is a function which is function of a variable. f2 now is a function of x and x itself. So if I write f1 is equals to x squared and f2 of x equals to x squared, both means the same thing, but when you want to substitute, then the process is different. If you want to substitute in f1, the value of x equals to 2, you'll have to write this command, v1, which is substitute in function f1 in place of x with 2. So instead of f1, wherever x is given, it will replace it by 2. So the value becomes 4. While v2, when we already have defined that f2 was a function of x, so we just need to write f2 bracket 2, replace x by 2. Let's say we define one more function, which is x squared plus 2x plus 1. Now, we want to solve this quadratic equation. So we want to set it to 0 and find the values of x that satisfies that equation. So one way is to write f solve is equals to solve f set to 0 and solve for x. So it will replace this equation equals 0 and find the solutions of x. So we know this is x minus 1 whole squared. So the solutions are minus 1 and minus 1. But if we want to solve it numerically, for some time, there's an analytic equation. Sometimes for analytic equations, the solutions are not possible. So we have to calculate it numerically. So if we want to calculate it numerically, then we use VBA solve. Then we don't need to put equals to 0. It is implicit. And we don't need to specify which variable to solve. Even if there are so many variables, it will solve for each of them. Now this is the most powerful thing of symbolic math toolbox. We can define derivative and integral of a function. Again, we define symbolic function f, which is a function of x. We write f of x as x times 1 plus x plus 2. How we differentiate? We use differentiate command, diff. So f diff is defined as differentiating command. F is used for differentiating. F of function f of x with respect to x. So this complete statement will differentiate f of x with respect to x once. This is the answer that you'll be getting, 2x plus 1. You can do the hand calculations and verify. Very easy. Now we go to integral. For integration, we use this int command, f of x with respect to x. So this is an indefinite integral. Sometimes it can happen that the indefinite integral is not possible. Then it will return the same function. So here, integrating f of x with respect to x, we will get this. But to just cross-check, what we did, we took the differentiated function, integrated it with x. So we get f of x plus constant back. Since it's a indefinite integral, so it will vary with the difference of a constant. Again, you will be getting ff equals to x times x plus 1, which earlier was x times x plus 1 plus 2. We can see that f of x and ff differ only by a value of constant. So this means that the differentiation and integration are exact. We can also calculate limits. Or let's say for tan x, instead of x, we want to calculate the limit at pi by 2 coming from left hand side. This is the left hand limit. The answer is infinity. Similarly, from right hand side, if we come, it's minus infinity. Hence, if we don't put anything, it has to calculate the limit at that point. Since left hand limit and right hand limit does not match, hence the limit does not exist. The answer is, we can also have a Taylor series expansion. Let's say we have a function sin x by x and we want to expand it using Taylor series. So this is the Taylor series expansion. Also, we can use this to solve ODE. Let's say differentiation of x. This is dy by dx equals to minus a times y. So if we solve it, it will come out to be c1 e to the power minus ax. Given proper boundary conditions, this can be exactly solved. If we have some large expressions and we want to simplify it, then we can use simplify command. So here you can see we have a large algebraic equation with variable powers of x, and we want to simplify it. These are in terms of factors. So the simplification comes out to be x to the power 12 minus 1. So we can use this combine command. So it combines this trigonometric equation in terms of sine cos. So the answer becomes sine 2x plus 1. Similarly, if we have some expression in y and x, we want to factor it. So we can use factor command. We can also have some complicated expression as well. In most of the cases, factor command gives us the relevant factors. So if I have a function f of x and I want to rephrase it in terms of another variable, so instead of x, I want to write y minus 1. So we can use this command, expand f y minus 1. It will replace first in terms of x, y minus 1, and then expand it to have each term with some coefficients. So this is the final answer. Also, sometimes it can happen we have two functions and we want to calculate the composition. I have an f of x which takes in the input x and gives us the output square root of log x. Similarly, a function g of x which takes in the input x and gives us square root of 1 minus x. I want to create edge of x, which is f of g of x. So first it takes the input x, then creates g of x, then g of x becomes the input for f of x. So this is the final result. Now plotting symbolic expressions is much easier. The functions here are different. We use the command fplot to plot different functions. I have defined a symbolic x, then I can straight away plot sin x, cosine x, and tan x. So here you will see these are the different plots. Now we can also do a parametric plotting. I define two different variables, x and a, where x is the primary variable and a is the parameter. So I define an expression which is a times sine of x. I play with a. So for f plotting, I would do substitute in the expression. In place of a, substitute it with 1, 2, and 4. And plot this whole expression between 0 to 2 pi. Also show the legends. Earlier we had to describe the legends. Now it will take it automatically. So here you will see the plot. This is the sin x. This is a equals to 1. Then this is a equals to 2. And this is a equals to 4. Plotted between 0 to 2. Completes a full cycle. Also we can plot implicit functions. Let's say we have a function of type f of x of y equals I. Then we can have implicit plot. It's slightly different from a parametric plot. So it is a function of two variables equaling some constant. And this constant is different for each case. So again, I am plotting using f implicit command. Expression x squared plus y squared equals to r squared. Here r varies from 1 to 10. And the axes are from minus 10 to 10. And the axes are squared. So in x and y, both the axes should be same, from minus 10 to 10. So this is the implicit plot command. We get this concentric circles centered at origin. Now we can also plot contours of function, f contour, using f contour. See, contour, what do we mean by contour? So contour is, we have some, think of it like, you have different mountains. And then you cut that mountains in slices. So if you have a mountain of height, some kilometers, and you just make some slices at each level. So whenever the boundary of the mountain intersects that plane, that is represented as contour level. So here, you see that this yellow line means this value z equals to 6. If z equals to 6 was passed through this surface, only this yellow part will be intersecting with the plane. Similarly, if we go to minus 6, all these blue lines will be intersecting with the plane. So whenever you see this, whenever you see circles or something approaching a circle, you can think they are approaching either a maxima or a minima, depending upon the color scheme. So it is plotted using f contour. You give the function, then you give the x-axis and the y-axis. Minus 3 to 3 is the x-axis, minus 4 to 4 is the y-axis, and the level list from minus 6 to 6. You go from minus 6 to 6 in steps and then see the contours and then plot it on a single plot. Color bar is on whenever you need to show this color bar, this command is used, and the title. So these are the basics of symbolic math toolbox, which can be very helpful whenever you are doing some analytical formulations. This is in competition with Mathematica and MAPL, where one used to have the analytical expressions and the derivatives and integrals of those complete formulations, and after calculating the final expression, they need to put back the values in MATLAB. Now, using symbolic math toolbox, there is no such need. You can do everything implicitly in MATLAB. So this is a very powerful tool, and once learned, it can be very useful to you. So I hope you learned something today, and you can straight away go to MATLAB and practice a lot of problems using symbolic math toolbox. This completes the basics of MATLAB required to start programming. Now you are, in a sense, literate about MATLAB. Now you understand how the MATLAB works, how different commands operate, and how to interpret different commands. Now we can go to problem solving and learn logic building and how to convert a big problem into smaller chunks, convert it into small reusable functions, which can be used to create large programs that can be helpful for solving mathematical problems computationally. So in the next video series, I'll start teaching how to use these MATLAB tools and create a finite element library that can be used to solve different types of computational problems under different types of boundary conditions. So stay tuned and thank you for your time.